All right, so valence electrons and ionic compounds. Remember, ionic compounds are created by transferring electrons from one atom to another. Typically, we talked earlier about how we would have nonpolar, covalent, compounds. We have polar, covalent compounds, and then we have ionic compounds. Okay? Typically, they will come out, this is kind of like a number line almost. Typically, you will have compounds that have, like if they're sitting here, remember it's the electronegativity difference that determines kind of where they fall in this. And you can have polar covalent compounds that have certain characteristics of ionic compounds. So the closer they get to becoming an ionic compound, the more character they're going to have of this. Now, what characters do these have? Typically, these have very, very high melting and boiling points, like table salt, for example, as opposed to something like table sugar that would have a much lower melting point. Okay. Your nonpolar covalent substances do not dissolve in water. These do. So you have kind of representative characteristics of these. And we'll get into those more, especially the covalent ones, more when we get into Unit 2. Okay, this is your VSEPR structures, your hybridization, things like that we talked about last year. Remember these things? VSEPR.
Is that like with the angles?
Mm-hmm. Yep. So when we look at electronegativity differences, you're going to be seeing here the electronegativity difference would be 0. Here it starts around 0.4, and when you get up to this is about 1.7 electronegativity differences. Okay, so if you look back at the notes, I had given you a chart in the notes. We had talked about electronegativity differences here. No, not here. My bad. Here. Okay, and we had said, you can go to the bathroom. We had said that this electronegativity was 4. This was like 3.5. This was 3. This was 2.5. This was 2. And this was 2.1. And then everything that comes after this is probably around, this ends up being like a 0.7. Yeah. So if you have these, I believe this one's like a 3.5. As you move this way, it becomes less. And that's what we wanted to kind of get. Now, why is hydrogen so weird? Because remember, it's not a metal. It's stuck over here because it has one valence electron, but it's not a metal. It's your one kind of outlier in this section. Okay? So the rest of these are metals. This one is not. That's why its electronegativity different, or electronegativity is so much higher than the rest of the metals over here. You don't have to memorize these values. Again, it's easy, I think, if you know that this one's 4 and it just kind of cascades down from there. And you can kind of use these to determine what type of bonds you have, but it's not necessary. All right. So when we're talking here, oops, I guess I went too far. My apologies here. When we're talking here about these compounds, you can use these electronegativity differences to find out where it kind of falls on this. Okay. Now, what does it mean to be polar covalent? Well, when you have a polar covalent compound, like for example, water, that means that the electrons are going to spend more of their time when they're shared at this end of the molecule. So this is going to have a negative charge, and this is going to have a positive charge. This is a Greek symbol that means charge. The other way you can draw this, when you're drawing these molecules, and we'll get into more of the drawing next unit, so don't worry about it too much, is you can draw an arrow and put a plus at the end of the molecule that is positive, and then that points to the negative end of the molecule. Okay, so this is polar. That means that when it comes up with another substance that is also polar, the negative end of that one gets attracted to the positive end of the next one. And that's why you get surface tension on your water. That's why water has a higher boiling point than, say, alcohols and stuff like that, because this is a much more polar molecule. And we'll get into more of that as we move through the units. When we're looking, and that's what they're doing here, is looking at ionic compounds, that's going to transfer an electron. So for example, if we had sodium, remember sodium has one electron in its outer valence shell. It's going to have 8 here and then 2. So its first shell has 2, this one has 8, and this one has 1. If we look at chlorine then, chlorine is going to have 2. That looks ugly. Sorry, guys. Let's try that again. Chlorine is going to have 2 in its first shell, 8 in its next one, and 7 here. Okay? To get this to be a complete shell, it's going to take this electron. That electron is going to get transferred over here. Then sodium will have 8 because we took 1 away. And chlorine will have 8 because it added that one in. And that's how sodium chloride forms. It transfers that electron over. So an ionic bond always involves the transfer of electrons from the least electronegative species to the most. In other words, from a metal to a nonmetal. Okay? So traditionally, ionic compounds are described as being between a metal and a nonmetal. Based on electron configuration, elements will either lose or gain electrons in order to have a complete outer shell. Loss or gain of electrons then leads to a formation of a positive or negative ion. Ionic compounds are held tightly together by electrostatic forces, so the attraction between the negative and the positive. So when I taught you this back in the day, I told you 1, 2, skip a few, 3, 4, 5, 6, 7, 8. Everything wants to be like this. And it's either going to give 1 or 2 electrons, maybe 3 electrons away, which means it's going to bump back up to the previous row, or it's going to take electrons. Here it would take 1, here it would take 2, here it would take 3 to look like this. That makes sense? It's going to transfer those electrons. Yeah. What about 4? 4 typically will end up sharing. So that's why carbon is, it's a 4, and it typically will form covalent bonds. Not always. You'll sometimes find it with other ones. So for, but typically it's going to share. And these guys will share with themselves too. So this guy will share and form with this, and you'll get a bunch of that. And that's what Unit 2 is pretty much all about, is that sharing. And if you get into college and you take more advanced chemistry, like organic chemistry is carbon-hydrogen bonds. And it has these carbon-hydrogen bonds, and that's what you study. And that's all sharing. That's all covalent bonding. And that's pretty much all of your biochemistry. So all of your DNA, your proteins, your carbohydrates, your lipids, all of those involve this, and that's what organic chemistry is all about. And it's that sharing. So we have to have neutrality. So the number of electrons lost has to equal the number of electrons gained. So when they're lost, we're going to have basic kind of electron configurations that form that give us a noble gas configuration once they've lost or gained electrons. Now, when we look at these, typically you're going to find things in the same column forming the same ratios. So for example, if we had calcium fluoride, this would give up 2 electrons, and you would need 2 of these to get those electrons, because this can only gain 1 electron. So your calcium has 2 electrons to give away. Your fluorine only needs 1 electron. So in order for this to balance, you would have to have 2 fluorines to take up those 2 electrons. So your formula for this is CaF2. If we looked at magnesium instead of calcium, what would its formula be with fluorine? Well, it's the same thing, because magnesium is going to give away 2 electrons. So that's what they're saying here. As you, in the same group, they're going to form the same type of bonds. If we go down and do strontium, strontium is going to look the same way. We just change this to SR now. So everything in that column will form the same type of bonds with everything in the fluorine column. If we mix that up and change this to chlorine, you're going to end up with the same formula then. Does that make sense? Okay. That's what this is about. I just went through that. So we want to have, we want to end up with those noble gas configurations. All right, so calcium reacts with a certain element to form a compound with the formula CaX2. They're just representing this with that thing. What would be the most likely formula for that compound to be formed with between sodium and element X? So now we're changing, we're going to have sodium and X. So calcium had 2 electrons to give away, right? And right, so X would have been able to pick up 1 electron. So that means that this is 1, 1. So this would have come from what column? The 7th column. So D would end up being your answer here. It's all ratios is all it is. All right. We're talking about this guy right here. All right. They would have. It would have been a lab down there, probably in Oak Ridge. Is my guess. Which is near Knoxville. Huh? I don't know which one was the latest. It was one of these guys down here. Yeah.
So are they done with all the elements?
Well, I'm sure somebody's trying to make 119, but who knows?
Oh, they just want to start a new road, the little mean.
All right, so we're trying to figure out what the noble gas configuration of this would be. So is it going to gain an electron or lose an electron to get a full octet? It's going to gain. So its noble gas configuration would look like this, the original gangsta.
Why don't we ever
OG. Okay, so if we're looking at noble gas configuration, that means that I'm going back to my previous noble gas. So I'm going to have Rn here. After Rn comes francium. So francium, remember this is 7, so that would be 7s2. This is 86. Where does or 88. Where does 89 come in at?
Acting on
Right down here. So this is period minus
it.
2. So 7 minus 2 is 5. F, I need all 14. After that, I'm going to come up here. So this is period minus 1. So 6D10. And then I'm finally coming over to here, 7P6. Now we need to make this with magnesium. Magnesium has what charge? How many electrons would it lose? 2. So if it loses 2 electrons, it would be plus 2. We're going to put it with Tennessean, which is here. What charge would it have if it gained 1 electron to look like this? Minus 1. If I want to balance these charges out, how many of these would I need to balance that plus 2 out? 2. So my formula would be MgTs2.
Party. Is that all we're doing today?
I believe so. I believe we are done with Unit 1.
So we get to party when we're done with all this stuff?
In May, yes.
No, yeah, okay, I didn't know this. LLB party with me. Answer the question.
You need to go? Okay. I'll have this recorded. You can watch it. Do you need us to take your stuff for you? Do you need to go to the nurse's office? Okay. Do you need the nurse to come get you? No? Okay.
Whoa, you still got